الحمد لله بخير. كيف حالكم يا شباب؟ أخباركم إيه؟ إن شاء الله بخير.
اللهم لك الحمد. تمام.
الحمد لله. آمين. So far we've been looking at the issue of properties of opaque surfaces. And by opaque surfaces, what we mean basically is the receiver or the absorber of the solar collector. The solar collector normally would be made of an absorber plate. On top of the absorber plate, we can have channels or tubes where a fluid is passing to be heated. And in many cases, this receiver is covered with glazing or a glass. Sometimes it does not, but most of the collectors that we know that we are using are covered with glasses. Those that are not covered with glasses are the ones that can be used for heating water in swimming pools, for example, or so, where you don't expect to heat it to a very high temperature. But if you are looking for considerably higher temperature, 70, 80, even 60 degrees centigrade, then normally they are covered with glass. So far, we are talking about the surfaces that are opaque, surfaces that do not transmit the energy through, so that they are receiving the energy and they are transmitting this energy by conduction, by convection to the fluid. The last thing that we're discussing out of these surfaces is a property which is being characterized for what we call selective surfaces. The selective surfaces are the surfaces that can have high absorptance in receiving the energy. On the other hand, they do not emit the energy, especially associated with long wavelength radiation or lower temperature case. So these surfaces can have characteristics that can be seen in a figure like this. For the solar radiation, the distinction between the long wavelength and the short wavelength is about a wavelength of about 3 micrometer. So below 3 micrometer is the range of what we call short wavelength radiation, which is basically associated with solar radiation. It's coming from the energy of the sun. And you can see here that the value of rho is low, which means that the value of alpha, which is the absorptance, is about 0.9 for such a case. So it is absorbing 0.9 or more of the energy falling into it. However, when it comes to emittance for a long wavelength radiation for greater than 3 micrometers, the value of rho is too high, which means that the value of epsilon or the emissivity is quite low. Here it's something like 0.05, which means that it is not emitting radiation except for about 5% of the amount of energy that it holds. The 3 micrometer is not a magic number, which means that it's not exactly at this value. It's normally, there's some sort of an overlap, which means that the short wavelength radiation can extend a little bit above the 3 micrometer. Similarly, the long wavelength radiation would extend a little bit below the 3 micrometer. So what we have here is some sort of an idealization of the process just for the sake of clarity, and we'll be able to see figures that represent the real cases, maybe after we cover that example that we started last time.
Victor,
Yes.
so how to get such a property?
This is what we are going to talk about in a while. So we are going to have an example, assuming that this is happening, and then let's see what we can do to the surface so that the surface can have this idealization or idealization as a selective surface. So we're coming to that by having a special coating that can happen to the surface, and accordingly, you can maximize the short wavelength radiation reception in terms of absorptance and minimize the amount of emittance of the surface. So here we're talking about a surface which is characterized by this figure. What we are supposed to do is to calculate how much is the absorptance of a black body or coming from a black body radiation of which is the sun at 5777 Kelvin, and also calculate the emittance at surfaces temperatures that are 150 and as well as at 500 degrees centigrade. The absorptance of radiation from black body at the sun's surface temperature is found by equation 464. I've covered this equation before. And again, I would remind you of one of the key takeaways from this figure, from this chapter, is that although the figure is not providing us with characteristics of alpha, it is actually given in terms of rho. And we know the relation between alpha and rho, which is specified also in this figure, that can be given for using the tables that we have that we had before, like table 361, where the values of the fraction of the energy falling is being given in equal intervals, and that's basically what we're going to do. We're going to look at the values of the delta phi rho for the range of lambda that we have. So alpha basically is alpha short wavelength for the fraction of the energy from 0 to lambda t, and lambda here is the lambda that basically does this kind of distinction between the short wavelength and the long wavelength. It is this line. So the lambda, which is the 3 micrometer that we are considering here. So we're considering alpha is first the value of alpha characterized by this portion and then the other portion as well, or as if it is cut into two pieces here. So for alpha is equal to 3 micrometer and a temperature of 5777, then the value of alpha T is 3 into 5777, which is equal to 17,331. For a value of alpha T equal to 17,331, we go to the table and you'll find that we don't have this value specifically, but we have 17,000 and 18,000. And this is why we need to do some sort of linear interpolation. This is the value of lambda t, whereas the other figure or the other line here represents f from 0 to this lambda t. So the value that we want is 17,331 minus 17,000 divided by 18,000 over 17,000. It is going to equal to the value of f from 0 to lambda t that we want. We call it x minus the corresponding to 17,000 is 0.9776 divided by that corresponding to 18,000, 0.9807 minus that value, 0.997 here. So from here we can calculate the value of x. X is equal to 0.9786, which is approximated as 0.979 as per the examples being given. So that's the original of the word of the number that we have here. This parenthesis actually it should be the corresponding value of alpha, which is 1 minus rho, and the rho is 0.1 in that range. So 1 minus rho, which is alpha, into that fraction of the energy at that range, plus the value of alpha, which is 1 minus rho, which is 1 minus 0.95, into the integral from 3 to up to infinity, which is given as 1 minus 0.979, the value that we got here. From here, we can calculate the value of alpha for the surface, and it's equal to 0.88. So this means that this surface is able to absorb 88% of the energy falling into it from the sun. And what it will not absorb, what it will be reflecting, or the losses here are going to be in terms of 12%. Are we going to lose this all? That's another story, because this quantity that is going to be emitted, it's going to be reflected. Actually, it's going to be coming from what we call a low temperature surface, and we have a glazing, we have glass on the top, and glass is opaque. This is the greenhouse effect that we talked about in the introduction to the course. Accordingly, even the 12% here with a cover of glass are not going to be totally lost to the surroundings. It might be used for heating the glass, for example, or if we have like a participating medium within the solar collector space that can be used for heating it. That's something that maybe we'll be looking at in our next chapter. Now, the second part is we need to calculate the value of the emissivity at these low temperatures. One of them is 150 degrees centigrade. The other one is at 500 degrees centigrade. So we're going to do the same by measuring the emissivity by the same principle of, or the same procedure, but knowing that we're talking about our absorber surface is at 150 degrees centigrade, which is basically 150 plus 273 to change it into Kelvin, so it's 423. So 3, which is the distinction of the wavelength, multiplied by 423 is a lambda T of 1269. Similarly, we don't have the 1269, so we're going to come here somewhere in between the 1200 and the 1300 and do interpolation to get the value of F. And that's what happened here. And the value of F is equal to 0.004. Accordingly, 1 minus 0.1, this is the value of the emissivity, 1 minus rho for the wavelength less than 3, multiplied by this F, and then 1 minus rho for the wavelength greater than 3, and the remainder of the integral, which is basically the value of F from 3 up to infinity, which is this, and it will calculate an emissivity equal to 0.05. So energy falling into that surface has actually heated the surface, increased the surface temperature. The surface temperature reaches 150, although it is at 150 centigrade, but it emits only 5% of the energy that it has. So it is receiving 88% and it is only emitting 5%. If it's at 500 degrees centigrade, then the temperature is 773 Kelvin and lambda T is 2319, and we do the same calculations, you'll get an emissivity of about 0.16 or 16% of the energy that it holds. So we have a surface here which is receiving 88% of the energy and emitting somewhere between 5% to 16% depending on the temperature, which means that the surface itself is getting the benefit of that property of selective surfaces in a way that it is receiving a substantial amount of radiation and emitting only a smaller quantity of it.
Doctor,
Wavelength dependence on or the value of rho as it depends on the wavelength is not as ideal as we have seen in that figure, as I just stated a while ago. But for real surfaces, it can take different shapes, which are not that sharp in change as we have seen in the previous figure. But they would be looking to some extent like this, which means that it is not really a straight line here, a horizontal line and a horizontal line here, but it experiences this kind of characteristics. And here we have basically the surface A is a surface which is polished zinc on polished aluminum. So basically aluminum is being polished and you have a coating of zinc on top of it, or you have a galvanized iron with a coating of a commercial material on top of it. It's called MIL. And the lower one, again, we're talking about galvanized iron, which is being treated chemically. So these are surfaces that are being adjusted by having the surfaces made of a certain material. The most common of them could be, for example, using galvanized iron or galvanized steel. Most of the kind of units that we are using because they are cheap for the materials or for the tubes of the solar collectors. The other figure here is again showing the reflectance of black chrome on dull nickel. So you have nickel and you're coating it with black chrome. And this is being tested in humid or a non-humid material environment or atmosphere. So the values here are showing low values of reflectivity at a certain wavelength, and the distinction is not really a straight line, but it is gradually increasing to a high value for high values of the wavelength or the short wavelength, the long wavelength radiation, which is corresponding to relatively smaller temperature of the surface. Smaller temperature, I'm talking about the order of 100 to 500 or so. Methods of preparing the selective surfaces were developed, and they depend on a combination of the mechanisms to get the selectivity. The combination of mechanisms. What are the mechanisms we are looking for? We are looking for being having high absorptance for short wavelength radiation and low emission for long wavelength radiation. So these are the two mechanisms that we are looking for. Upon so many trials, they came up with this kind of coatings. We have seen examples of coating, whether the coating can be done by zinc or by chrome. So that's something that depends on the material that you are using, and definitely the economical factor comes here as an important one. The coatings absorb the solar energy, and the substrate, which is the basic material, is the one which is a poor emitter. So you have a combination of the two properties this way. These coatings may be homogeneous, or they can have a particular structure. Now, as trials with the industrial fabrication of these coatings is being advanced, so several ways of having the coating applied on the surface can result in more advanced or better kind of characteristics of the surface as being a selective surface. Again, some examples are given here. Copper oxide can be coated on aluminum, and copper oxide can be coated on copper, and using copper or copper oxide coating on copper. This one I can see, or I can anticipate that it has so many of the share in the market, because normally we prefer to use copper tubes in the solar collectors as long as you are heating water or heating ethylene glycol solution, for example, because copper has a high thermal conductivity, which means that the energy that is held by the selective surface, by the plate of the solar collector, can be transmitted by conduction. Conductivity is high for the copper, and then by convection from the copper to the fluid inside. Again, nickel zinc sulfide coating is another example which is being applied to galvanized iron. So this table again is showing the values of alpha and epsilon for different combination of these surfaces with or coated surfaces, where the basic or the bare surface material, for example, black chrome on nickel plated steel, sputtered cermet coating on steel, or galvanized. So that's basically a combination. You can see here they are all characterized by having high value of alpha for short wavelength radiation and quite a small value of epsilon for long wavelength radiation. So optimum properties, it becomes optimum as the value of the absorptance increases and the value of the emittance decreases. It is not only a function of the wavelength, by the way, but sometimes it's a function of the angle at which the solar energy is falling into the surface. For example, you can have a figure like this, which is showing how the incident angle can change the value of alpha. And even a polynomial fit for this line is given at the bottom here. You can find that it is the value of alpha over alpha normal. Normal, that the solar energy is coming normal to the surface, and the value theta is the incident angle. So as the value of theta changes, the value of alpha also changes, as you can see it here. So alpha decreases as the value of the incident energy increases, or the incident angle. Accordingly, it's better to have it as normal energy falling into the surface. So again, how can we make it normal? It can be done, for example, by tracking. So it's just a matter of a trade-off. You see how much tracking is going to cost you, and how much energy you are going to get, and you just compare that. Is it better to increase the number of solar collectors with stationary position, or maybe use less collectors with tracking? Tracking, you know that it needs additional material, it needs additional power for a tracking motor and a mechanism that can control the motor for tracking based on the motion of the sun in the sky. So that all are parameters that should be kept in mind while you are making this selection and uh, deciding the number of collectors to be using and the way that you are going to use the collectors. This is a part here which is left to you for general reading, which is the section 12, absorptance of cavity receivers, as well as the issue of specularity reflecting surfaces. That would conclude our talk or discussion for the radiation on opaque surfaces. So this is basically the base of the solar collector. And what we need to turn focus into is the glazing or the glass, which is making the solar collector. So, which is basically the start of chapter 5. And I will probably get it uploaded and then share it with you here. So in this part, we are going to look at radiation transmission through glazing. So by that, or by completing chapter 5, we could have looked at the radiation characteristics, the relation of angles of radiation, the change of radiation throughout with time, I mean with days or with months, averaging it, the relation with extraterrestrial and terrestrial radiation, and finally looking at the kind of surfaces that are receiving the radiation, be it the absorption surface, which receives the heat and transmits the heat to the fluid that it is heating, and finally here the cover or the radiation cover, the glazing or the glass. It's not only glass, as we will see, is basically used for covering solar collectors, although the glass is the cheapest and it's the one which is mostly used as a cover for solar collectors. The surface properties that we have been dealing with, even lately with the surfaces, are basically the transmission or the transmittance, the reflection, the reflectance, and the absorptance. These are the main surface characteristics as when it comes to radiation. When we are talking about glazing here, then we are going to consider the one that we have been neglecting so far, which is the transmission or the value of tau, as the glass is allowing the energy or the radiation energy to go through. It may have less reflection and less absorption, and this would be the needed characteristics for glass. We need the glass to transmit as much energy as possible. So transmittance here is our key property that we are looking for. Those properties, transmittance, reflectance, and absorptance, are dependent on the incoming radiation, the thickness of the glazing or the glass, the refractive index for the glass, and the extinction coefficient. Now we are being introduced to some new definitions. As you can see here, we are talking about the refractive index. We are also considering the extinction coefficient, and we are going to have another definition here for the glass, which is basically talking about whether it is polarized or non-polarized. The refractive index and the extinction coefficient of the cover material depend on the wavelength of radiation, Although, for the sake of simplicity in this chapter, we are going to consider them as independent of lambda. The dependence on the lambda uh, is not significant, especially for glass, which is the most common type of solar collector cover that's being used in industry. Some cover materials also have some optical property variations with the wavelength, and their spectral dependence is given in this chapter as well. The incident solar radiation is basically unpolarized or slightly polarized, and we're going to look at this in a while. The polarization considerations are important because radiation characteristics can change being polarized or non-polarized as it passes through the collector covers. Now, in this slide, we have seen like three new definitions to us. One of them, we are talking about the refractive index. You'll see that it's not new. You have covered that in physics before. Extinction coefficient is another definition. And the third one, talking about the unpolarized or polarized glass. I looked first at some sort of a formal definition of these properties, and it's been shown here. The refractive index of a material is a dimensionless number that describes how fast light travels through the material. It is defined as n, which is equal to the ratio between the speed of light in vacuum and the phase velocity of light in that specific material. If you remember, you have studied in physics before what we call انكسار الضوء, that the light uh, ray can come at a certain angle, and then after passing into a different medium, the angle changes. Then the extinction, they also call it attenuation coefficient, which means that the solar ray gets attenuated or reduced as part of it is being absorbed in the material, in the glass, depending on the wavelength and the mass density of the glass. Then, the polarized light waves are the light waves where the vibration occurs in a single plane. This is what we call polarized. What we are getting from the sun is a non-polarized light. So it has vibrations in all directions, in all the planes. And then you may have your glass that can change these characteristics from unpolarized to polarized. One very good example for the issue of polarization is the sunglasses, especially if you are moving in an area where the ground is white in color or it is reflective. Then you find that it is hurting your eyes if you don't wear the glasses, because you have energy coming from the sun and you have reflection, which is coming from all, the wavelength or the waves that are coming, or the electromagnetic waves are having vibrations in all directions. You can attenuate that, you can filter it by having sunglasses that allows only, or that polarizes the energy which is coming from the sun. There are like 3 videos that are having excellent explanation and given some sort of like lab or even some sort of out of the lab experiments that are describing these properties in a very good manner. I put a couple of links here in this slide. So I urge you to understand this issue of polarization and how you can control that. And again, the issue of having linear polarized lights, or even circular or radial polarized surfaces or glazing. And it even explains the way that how our eyes can be tricked so that you can have some sort of polarization in one surface, like vertical and horizontal polarization in another surface. And one of these surfaces can make the left glass of your eyeglasses, and the other one can be for the right glass. And then it fools us so that it makes like a phase change or a phase shift. And then you can see something like 3D. And that's why you have a special kind of glasses if you are going to the movie and it's a 3D kind of film or that you might be seeing. That without the glasses, you can see that the skin is blurring. I remember when they started Isra, which is nearby here, they have like a 3D movie that they were showing. It was some sort of a trial, and the movie was scientific in nature, so it was some sort of a documentary, but it was shown in a 3D arrangement. And we just received the glasses when we went into the theater. The film has started already by that time, and then without glasses, without these special glasses, it was blurring. But once you put it in, you can see some sort of a 3D. So the eyes have been tricked by this kind of change in the optical characteristics of these surfaces. Not necessarily glass, but they are having this kind of characteristics. So a couple of videos are shown here, and the last slide of this presentation has a third video, which is also an interesting one that I would urge you a lot to see it. It's very beneficial, and they are very interesting as well, because you are going to look at some experiments that are being done in front of you, and you can see the effects of these. Now, this is the kind of refraction that I'm talking about. You see, and probably you have seen that in physics, maybe, that the solar radiation or the radiation is coming here, and when it comes to the water going from medium 1, which is air, to medium 2, which is water, then the angle of the rays changes. So for smooth surfaces, Fresnel has derived expressions to estimate the reflection of unpolarized radiation on passing from medium 1 with a refractive index N1 to medium 2 with a refractive index N2. And the parallel component is given by R parallel. The normal component is given by R normal. So we're using that symbol here as a subscript for the normal component, and this symbol here is used for the parallel component. And you can calculate the normal and the parallel component based on the equations 1 and 2 that we have here. The total refraction here is a combination. Actually, it's an average of both of these, which is, by definition, it's the refractive energy divided by the original incident energy, and it's given as a combination of R normal plus R parallel divided by 2. So the equations here are representing both perpendicular and parallel component of unpolarized radiation. Equation 3, or 513 here, it gives the reflection of unpolarized radiation as an average of both of these. So these are values that, or these are expressions or equations that we can use to get or to calculate both the perpendicular as well as the parallel component of radiation or falling radiation into the surface. One more relation, which is Snell's law, that gives a relation between the angles here. So N1 sine theta 1 is equal to N2 sine theta 2. And this is useful, for example, if the angle of incidence and refractive indices are known, and you need to get the other value, which is the value of theta 2. That's something that can be calculated easily from this surface. And then here we are looking at some special cases, and the special cases would be for radiation that is falling normal into the surface. So it's not coming with a value of theta 1 and theta 2, but basically theta 1 is 0. Look at this. Theta 1 is the angle between the falling energy and the vertical axis. So if theta 1 is 0, it means that it's falling normal. In this case, theta 2 also is going to be equal to 0. Accordingly, the value of the equation, which is basically 513, this equation, is going to be modified based on having these values are equal to 0, and it's been worked out so that the value of the reflection can be calculated based on the values or the refraction index N1 and N2. If the medium is air, then the equation is being also modified so that you can get your refraction and refraction with a component with with this expression n minus 1 over n plus 1 whole square. So this is the general expression that we have here based on the angle. If the angle is 0, then the equations modify to that expression. If the medium is air, then we can also have this expression as you can see it here. Let's do that through an example. Calculate the reflectance of one surface of glass at normal incidence and at 60 degrees. The average index of refraction of glass for the solar spectrum is 1.526. So we're talking about normal incidence here. So we're going to use that special equation, which is for theta is equal to 0. And that's why it's called R0. So the values here are basically n, which is 1.526 minus 1. So it's 0.526 divided by n plus 1 whole square. So it gets the value of the reflectance for this case. If the angle is 60, then basically we can make use of this relation here, which is Snell's law, to calculate the value of theta 2, and theta 2 has been calculated here. And accordingly, knowing theta 1 and theta 2, we substitute. What you see here is a combination of equations 5.1, 5.2, and 5.3. So, which means that in equation 5.3, if you remember, sorry, it's the normal reflectance plus the parallel reflectance divided by 2. So that's the normal reflectance, this is the parallel reflectance, and we take the average of them. These are all combined in one line or one equation, as you can see it here. Half into normal reflectance and parallel reflectance. So half of the normal component is 0.185, the parallel component is 0.001, and then the reflectance of the surface at this angle is 0.093. There's another thing here that we have overlooked, which was, what about within the thickness of the glass itself? The glass is made up of two surfaces, an upper surface and a lower surface. What happens? Energy would fall into that. There's a part which is reflected, and the remainder which is not reflected is 1 minus R. It moves within the material until it reaches the lower surface of the glass. And then part of it is going to be reflected. What is falling is 1 minus R. So what will be reflected is R into this component, 1 minus R into R. And the part that will penetrate through is 1 minus R of the 1 minus R. So it's 1 minus R squared. And this keeps on, if you are going to follow the ray, as it moves here, you can find that the values are being attenuated, or the values are being reduced by that factor. So in solar applications, the transmission of radiation is through a slab. A slab basically is a plate of glass that have two surfaces, upper and lower surface. So two interfaces per cover are calling losses of reflection. At off normal incidence, if it's not falling normally on the surface, the radiation reflected is different for each component of the polarization. So the transmitted and the reflected radiation becomes partially polarized. The third film or the third link I'm putting here is specifically talking about this issue, that you may have, actually it's the second one as well, that you may have eyeglasses in which in one surface it is polarized vertically or horizontally, and the other surface of the glass is having a polarization which is round. And that's an interesting thing that will that you can even see it practically. The issue with this, if I share these videos with you, you might be able to see it, but you'll not hear the voice. So that's why I would just prefer that you go through it just after the class if you have time, and run them. I'll make this available in the Blackboard. I'll make the whole file available there. So accordingly, it would be necessary to treat each component of the polarization separately. If we neglect absorption in the cover material, as shown in the figure 5.1.2, as we can see here, and considering for that moment only the perpendicular component of the polarization of the coming radiation. So this is what we get, 1 minus R normal is what we are considering here. So in this, we just assume that whatever is going from here to here is going to remain as 1 minus R. It will not going to be absorbed by the material of the glass itself. This is the assumption that we are doing here. Of this, and here it is explaining basically what would happen if you have 1 minus R normal passes through the interface. R into 1 minus R normal is reflecting back from the lower surface to the upper surface. This is what we've shown here. 1 minus R is falling here. What is reflected is R into 1 minus R. What if we have several surfaces, then the expressions are being extended here from equation 517 to 518 to 519, which is talking about the conditions where it is n covers of the same material are going to be used. And what is it that we are measuring here? We are measuring the transmission or the transmittance through the glazing. A direct example on that is being shown here, which is example 512. It's asking to calculate the transmittance of two covers of non-absorbing glass at normal incident and as well as at 60 degrees. So at normal incident, the reflectance of the interface from example 511 is 0.0434. What is that? I mean, just to remind you that if we are going to have the glass cover like this, and remember from our first example, the angle was θ1 is 60, and when we applied Snell's relation, we got the value of θ2 for that example is equal to 0.0434. So this basically came from the relation that we have seen in our second slide, that N1 sine θ1 is equal to N2 sine θ2. So the tau R, or the transmittance for this case, is given by 1 minus θ2 divided by 1, or you can see it here, the equation, 1 minus θ2 divided by 1 plus 2n minus 1 into R parallel, which is n here, we are talking about two surfaces. So n is equal to 2, n squared is 4, minus 1 is 3, and the value is given here. So from here, we can calculate the transmittance for such a case. This is if it's falling as normal. What if it's falling with an angle 60? Then again, we are going to take the two components. So what we see here is an application of equation 513 for the calculations of tau R. What if we have one layer or two layers, one cover or two covers or three covers or four covers? This has been already calculated for different values of the incident angles. So what we did in the previous example has been repeated for cases of one cover, two cover, three cover, four cover, just direct substitution in the equation. So any one of us can be able to regenerate this figure that you can see here, and it's being done for simple utilization. For the case of once you know the angle of incidence and you know how many covers that you have, you can correspondingly get the value of the transmittance. And this also tells how the transmittance is being affected by increasing the number of covers. Then definitely the amount of intensity of radiation which is falling is being reduced due to the reflection and partially absorption of the surfaces. It's not only glass which is being used with solar collectors as a cover, but we have different type of materials with different refractive index. Glass has a refractive index of 1.526. Polymethyl metacrylate would have a refractive index of 1.49. Polyvinyl fluoride is 1.45, and so on, reaching down to the polycarbonate that has a 1.6 refractive index. So here, these are different materials that can be used instead of glass when you are dealing with solar collectors. Glass is still the most available, the most commercially used, and it's basically the cheapest. That explains why. Glazing does not only refract the energy or reflect it, but it also absorbs part of the energy. To calculate how much is being absorbed, we are going to use this relation so that the absorption of radiation in a partially transparent medium is described by Boger's law, which is based on the assumption that this absorbed radiation is proportional to the local intensity of the medium and the distance between the two surfaces, which is the thickness of the glass, for example, that we are using. So di is equal to di is the change of I due to passing in the glass is equal to minus I k, a proportionality constant, which happens to be the extension coefficient, into dx. dx is the distance at which it's flowing, or it is moving, or the radiation is basically moving. So we're talking about a surface like this, and we are looking here at, this is the x direction in that figure, and as the radiation is falling here, we're taking a dx and seeing how this value is being changed, how the di, the change of the radiation intensity is being changed here. And it is being integrated from this value, say x equal to 0, up to L, which is the thickness of the glass. Doing this integration, then the value of tau, which is the actual value of the transmittance here, can be given the transmitted energy over the incident energy is equal to exponential of minus KL over cosine theta 2. A here is a reminder that we are only considering absorption losses in this case. The value of K varies for the glass depending on the glass type. From 4, it has a unit of meter to the power minus 1, or 1 over meter. This is for the water-white glass. What is the water-white glass? I'll just continue here, which appears white when viewed in the edge, to approximately 32 meter to the power of minus 1 for high iron oxide content of the glass, which is showing a greenish color of the glass. When you have a plate of glass and you are looking at that thickness, what we see here normally in the market is that when you look at that, you find a green line with green color, which means that the kind of glass which is available commercially is the greenish cast at the edge, which is basically high iron oxide content of the glass. We're talking about the optical properties of glazing. Glass basically is the most commonly used one. And the properties that we are looking at are basically, as usual, transmittance, reflectance, and absorptance. And you might remember the relations that we talked about, and you started considering it in physics as well as radiation heat transfer, that the energy which is falling on the surface is divided between part of it is being absorbed, part is being transmitted, and part is being reflected. So the component of the three properties together is basically tau plus rho plus alpha, and this combination is equal to 1. In the previous chapter, we talked about opaque materials. So tau is basically 0. And if you recall in chapter 4, we only dealt with rho and alpha. Even the figures that we dealt with, we just had the value of rho, out of which we can calculate the value of alpha or calculate the value of epsilon. Here in this chapter, we are particularly interested in the value of tau, because we need to make sure that the glass that we have is not basically refracting or attenuating considerably the amount of incident radiation into it, but it's transmitting most of it so that it falls onto the absorber surface of the solar collector. The relations are given here, and for the perpendicular component of the polarization, tau perpendicular, the relation that's used is being given here by equation 531. The value of rho is given by this expression, equation 532. And finally, the value of alpha, or the absorptivity, is given as in this equation here. So all of them, as you'll notice, they are given as a function of the transmissivity tau. Similarly to what we see here, also the parallel component can be calculated. So you can calculate tau parallel, you can calculate rho parallel, and you can calculate alpha parallel. The properties at the end is going to be a combination or an average value between these and these and these. The equation for the transmittance of a collector cover can be simplified, noting that the last equation of, or the last term of equation 531, this term can be assumed equal to 1, so that the value of tau normal is going to be basically given by that expression here. That's some sort of a simplicity, because normally this value tends to be very close to 1. Accordingly, for simpler calculations, this whole term can be dropped, and you can consider only this one for the sake of simplicity, as I mentioned. And accordingly, it's a combination. This value is called tau sub A. This quantity can be called as tau sub R. And then accordingly, the value of tau can be obtained as tau A into tau R. And this is an approximation here. And and this is satisfactory for most of practical applications, cover materials that are of practical interest. The ones that are being used for solar collectors covers are all having this kind of a value which is close to 1 for these components that we have here between the square brackets, and accordingly the square brackets as a good approximation can be considered as equal to 1. The absorptance of a solar collector cover can be approximation by letting the last term of equation 533 again be unity. So the last term of this equation also can be considered as equal to unity as a completion of the simplification process, and then the value of alpha can be basically 1 minus tau A. We will see an example where we can have a look at this part in further details, or we'll be able to apply it numerically. The neglect terms of equation 533 is larger than the neglected term of equation 531. We are comparing between these two values. Here, this is 1 minus r. This is 1 minus r squared, which means that the value that we have here is basically higher. R is a fraction. So if r, for example, is 0.1, then it's 0.2. This is 1 minus 0.2. But this would be 1 minus 0.04. So we're talking about the component here, which is neglected for the simplification, is greater in value, in a numerical value, compared to this value. The absorptance is much smaller than the transmittance. So the overall accuracy is accepted. What we are looking for here, why we are saying that we are doing the comparison, because we said here this value is bigger than this value, but the quantity of alpha, all of it, is small compared to tau. Accordingly, having a bigger value to omit here is not going to affect our accuracy, because the value of alpha in a way is small. Remember, we are talking about a glass, and for the glass, the value of tau should be as high as possible. The value of rho and the value of alpha should be as small as possible. So if this is small, fraction of the small quantity is also small. So it does not affect the accuracy of our calculations a lot. And this is going to be proved numerically through an example. The reflectance of a single cover then can be calculated as 1 minus alpha minus tau. The advantages of equations 534 to 536, which are basically this simplified forms of the equations to calculate tau, alpha, and rho, is that the polarization is accounted for in the approximate equations rather than the complicated expressions that we had earlier. Let's have an example that will show the solution of transmittance by exact equation and by approximate equations as well, which is this example that you can see here. Now, calculate the transmittance, reflectance, and absorptance of a single glass cover. The glass cover has a thickness of 2.3 millimeter and angle of 60, which is theta 1. The extinction coefficient of the glass is 32. So it's basically like a green looking glass when you look at the edge, having a coefficient of extinction equal to 32 meter to the power of minus 1. For an angle of 60, the extinction coefficient, optical path length product is given by KL over cosine theta square. So the value is 0.04894. Why do we calculate this value? Because we use it for the calculation of tau A. So the transmission tau A from equation 522 is given as exponential of minus KL over cosine theta 2. If you remember, this value have been calculated, and accordingly, tau A is calculated as 0.915. Then we are using whatever we have covered in examples 511, equation 531 basically is this equation, and this is the one that we need to apply. Now we are solving exact solution. So we are going to consider all of these values in. The values of R normal and R parallel are going to be obtained from our calculations of equation 511, which is the equation that we started at the beginning here. This one. So these values are going to be considered. Theta 1 is equal to 60. And according to the example that we have at the beginning here, we got a value of theta 2 equal to, what was the value of theta 2? In the example, it's being calculated in one of the examples. What is example 1 or 2? And the value has been calculated of theta 2 and then we are taking these two components together. The 0.185 is the value of, let me have a look at this here, which is basically R normal. So the 0.185 is the R normal, which is being applied here. And the value of the 0.915 is the one we have just calculated a while ago for the tau A. So this one is calculating the perpendicular component. Whereas in the example, we have taken the parallel component as R parallel equal to 0.001, and this is the value that we are calculating here. And remember, we are calculating the average, so or the mean value. So this one plus this one divided by 2. That gets us the value of tau equal to 0.786. Then we are going to look at equation 532 to calculate rho, and equation 532 is providing rho here as a function of R parallel, tau A. This is the normal component, and we are going also to calculate the parallel component and take the average of them. So rho 0.5 into the normal component here, R normal is 0.185. Tau A is 0.915, and then we are calculating it as 0.147. And then similarly, the value of alpha has been calculated. Again, we are considering perpendicular or normal component, parallel component, and the value of alpha is 0.085. So look at this glass or this type of material. It has a transmissivity or transmittance of 0.786. So 78.6 of the energy falling into it is going to be transmitted, 14.7 is going to be reflected, and 8.5% will be absorbed by the glass. The alternate solution here is the simplified solution, in which we are neglecting the terms that are close to 1. Accordingly, if you go to equation 531, then this square bracket part is going to be neglected. And equation 533, this bracket is going to be neglected. And we are going simply to calculate these simplified versions of the expression for tau as well as for alpha. So when we do that, you are going to calculate the value of tau as 0.771. Again, this is the normal component. This is the parallel component. The value of absorptance alpha is 1 minus 0.915, 1 minus tau A. And then rho is going to be the remainder. So 0.771, 0.085, if you add them together, and 1 minus this added value will get us the value of rho. Let's look now as a comparison between those. So here we have the value of tau is 0.786. Here it is 0.771. Here the value of alpha, 0.085. 0.085. The value of rho, 0.147 and 0.144, which means that this approximation is an acceptable one. The percentage error between this one and that one is not significant. And accordingly, we can consider this as a good approximation that we can use for our calculations. It makes it a little bit simpler to have. Now, we're noting here that even though the incident angle was large, it's about 60, and the poor quality of glass is being used in this example, still the value of tau is not that bad. We're talking about 77% or 78% of the energy transmitted through the glass. Equations 543 and 546 that we have covered earlier, this is 534 to 546, which is using the approximations, are being given or are being derived for single cover. They can apply equally to multiple covers as well. And the quantity of tau R should be evaluated from equation 519 and tau A from equation 522, where L is equal to the total length of the different colors that you have, or different layers. So if you have a different layers, just deal with the same equation and take the total length or the total thicknesses as your thickness in equation 519. What is equation 519? To remind you again, this is 519, where we are calculating the value of the transmittance for the different number of layers that we have. So it's been some sort of a direct substitution to the equations that are given. We don't have to look how the equations were derived. It would be a long story, but what we are looking for here is basically how to make use of these equations in certain applications of glass materials. Once we know the kind of properties that we need, for example, the incident angle, and we are able to calculate the refraction components, whether it is in the parallel or in the normal direction. And these are the two directions that we are considering basically for our application here. That's again, we're looking at the solar transmittance at an angle incident angles of 0 and 60 for two glass covers. Each one of them has a thickness 0.2 millimeter. The extinction coefficient of the glass, K, is equal to 16.1, and the refractive index is 1.52. Again, direct substitution here can get us this value. For one sheet, KL is equal to the extension coefficient into the thickness. The thickness here is transferred from millimeter to meters, and the value of KL is 0.037. And accordingly, the value of tau A can be calculated here. The value of tau A is 0.93. The transmittance accounted for reflection tau r from the previous example has been taken as 0.85. Accordingly, the total transmittance can be calculated according to the simplified form in equation 5.3 form as 0.79. And we have taken tau A at 60 degrees centigrade. From example 511, the value is 0.91. And accordingly, the calculations of tau at this angle is tau 60, at tau A at 60, and the total value of tau for these two surfaces together is 0.69. So again, with two surfaces, 70% still of the energy is able to be transmitted through the glass. In some of the solar collectors, they are coming with a double glass cover, not a single glass cover. What's the reason for that is trying to minimize the losses to the surroundings as much as possible. Some of them are coming with evacuation, like vacuum inside there, like the evacuated tubes, or as probably mentioned before, the evacuated flat plate collectors, which eliminate totally the effect of convection as well as conduction losses, and the greenhouse effect, or the low emissivity of a selective surface, is going to take care of reducing the radiation losses as well. So it means that these are kind of collectors that are being utilized to minimize the losses to the surroundings so that they can heat the fluid inside to much higher temperatures. If a normal flat plate collector can be used for heating water to 70 or 75 degrees centigrade, an evacuated tube collector can increase the temperature to something in the order of 130, 150. A flat plate evacuated tube collectors can even bring it to 180 or 200 degrees centigrade. I'm talking about this kind of collectors that are being used commercially available without going to the concentration of the collectors. I'm not talking about like concentrated type collectors that can bring the temperatures to values that are much higher than that. Probably go through the attendance quickly, just calling your names. You might have noticed that today I've just taken out the waiting room so that you can get in easily. I should have done that earlier, but anyway, that's it's been something that will ease your logging into the program. So sorry. Abdul Hadi, Abu Zaid.
Yes, doctor.
Okay. Then Abdullah Abu Shaya.
Yes, doctor.
Abdurrahman Al-Mashhaf.
Yes, doctor.
يوسف المحيش.
موجود يا دكتور.
عمار الثملي.
Yes.
حسين الوحيد.
Yes.
صالح البلاهي.
Yes, doctor.
عبد الله الدوسري. عمر الجوهني.
Yes.
عبد العزيز المقثوي.
Yes.
عمر الشمري.
Yes, doctor.
عبد العزيز الشهري.
Yes, doctor.
ريان الوداعي. فهد الزهراني.
Yes.
Okay. عبد الرحيم بيما.
Yes, doctor.
نواف كعبي. Anybody knows Nawaf? Last time he was not here also. So if you know him, just give him a call, make sure that he is fine. Anybody knows him?
I worked with him on a project before. I can send him WhatsApp.
Yeah, just make sure that he's fine because he just missed a couple of classes in a row. So,
Sure.
الله يكون بخير يعني. أحمد خوار.
Yes.
أحمد سندي.
Yes, doctor.
ياسر شيثل.
Yes.
Okay. Okay, so are getting closer to the real application of this chapter once we are through with chapter 5. Hopefully that would be on Monday. Maybe we have some issues to cover also on Wednesday, and after that we should be able to get into chapter 6 where the application is with. In chapter 6 we're going to talk about the performance of flat plate collectors. And then chapter 7 will be about the concentrated collectors. This is probably that would be the time where we can think of what has been mentioned in the syllabus as a special assignment, or we can call it like a term project. You do not have access to the engineering equation solver, unfortunately, EES. And having access to it through the labs is going to be, we tried it before, it was not a smooth thing to occur. So I'm going to have this assignment, which is the either the special assignment or the term project, as to be worked out through Excel, or I might also ask you to upload a software which is freely available on the market, in the internet. I mean, the software is called Red Screen. It's being developed by a Canadian company, and it has so many excellent applications. Maybe you can take one of applications and just put some ideas for you to go through, and I can even put it as some sort of optional so that you can select. Sorry, since I have. So the software is basically called Red Screen. So whenever you have time, you can download the software, and then maybe once we are getting into these, you can just find spare time, and where we can look at quickly on the menus of that software. Actually, the software handles so many things. We'll not be covering all of them in the course, but at least maybe we can take one or two applications that can be used in this software, and we can maybe demonstrate it, and then you can continue in it on some sort of a special assignment that will be given to you, inshallah. So that's it for today. Unless you have further questions or any concerns to discuss, then we'll see you next time, inshallah.
Doctor,
Yes.
can you upload the slides for chapter?
Oh, yeah.